Okay, a quick self intro. My name is Yang, and I'm from Uber's online data org. And my current focus is the cache. We are basically building the reliable and scalable caching platform for all the engineers, basically engineer teams at Uber. And we also aim to provide as seamless as possible user experience. Shawn?
Hi, my name is Shawn. I'm on the Yang's team. I'm focusing on the Redis backend, proxy, and also the clients. I will share more about our the lessons we have learned during our migration from Redis to the Redis classes.
Right. Here is the agenda. So first, we are going to talk about a few cache use cases at Uber. And then later, we are going to dive into our architecture. And I'm going to go over a few key components. Later, Shawn will going to talk about the lessons we have learned in production. Some of them are quite interesting. And we're going to end our talk with a roadmap. Okay. Cache actually plays a really important role at Uber. So imagine when you book an Uber ride, right? A driver can pick you up in a few minutes. And actually the cache plays a really important role in terms of optimize the driver and rider matching. And also when you go to the Uber Eats app, you will see a lot of personalized recommendations, right? It's powered by our machine learning platform, which is also backed by the cache platform. Of course, there's another layer of the DB cache. And then, one of the most common use cases many people also use is basically put the cache in front of a database. It will help to improve the latency and also reduce the cost for the database. Yeah. So, in terms of scale, I believe this already mentioned in our title, right? We operate around 1 billion ops per second at peak. So we right now have roughly 2,000 clusters in production with one SLA. And we have variety of the workloads. Some of them are kind of CPU intensive with a very minimal memory footprint. Some of them having a really large node footprint, and they actually give us different kind of trouble. Okay, this is the architecture overview of our current platform. I did not call out all the components, but I just highlighted a few key components. So the first and most important one is the backend. Our backend currently is running with Redis. We are moving to Valkey, of course. And as we all know that Redis does not come with its own control plane. So we do have our in-house control plane. Uber runs at a multi-region architecture. So the regional failover can happen. And we do have a service that is able to replicate the cache from one region to the other region. And also, we are kind of an internal platform team. We need to serve all the product customers, basically the engineering teams at Uber. And we also need to provide a client for them just to simplify the integration. And from other engineer teams' perspective, whenever they need a cache, right, all they need is to go to our self-served portal to provision the cache, and everything else is handled by us. Okay, this is our story of our backend. I know a Snap guy talk about the migration, right? We also did a huge migration recently, in the past 2 years. So we migrate our backend architecture from our old architecture. We call it T-Redis. It's basically a twin proxy plus a lot of a standalone Redis to the native Redis cluster architecture. It's definitely not a simple migration, a lot of learnings, and Shawn will share it later. But why we do this migration actually? So let's take a look at the architecture for the previous previous architecture. So twin proxy basically is like a proxy. We put it as a host agent. So basically it runs on every single compute host at Uber. But the compute host also runs a tons of other services, right? When they need to talk to the Redis backend node, they all need to have proxies through this stream proxy. So naturally, like this is a multi-tenant proxy. It has a lot of problems such as head of line blocking, noisy neighbor. That's why we decided to just go with the Redis cluster with direct connection. We manage like 2,000 clusters, so we have to automate as much as we can. Let's know where we can manage this manually, right? So we develop our in-house control plan to manage the life cycle of the cluster. The provision is usually self-service. And of course, when the instance is provisioned, the traffic can go up and down. So we have to do scaling, and we need to automate the scaling. And sometimes the hardware can go bad. We have we cannot have human to jumping to fix that hole, right? So the self-healing is also a big requirement. And when the instance is not in use, we should decommission it. And all of this is powered by our in-house control plan. So basically, every operation is a workflow, which will go through a cluster directly. And some of them are automatic with the periodic check, for example, the scaling and the auto-healing. Right now, the periodic check still happens not very often. For example, scaling is a daily check, and self-healing is kind of every 30 minutes. So we are planning to build a new continuous monitoring service to make it faster. The automation can solve a lot of problems, but sometimes the bad things can still happen. And we have to stay on top of everything. And therefore, we create a very comprehensive alert to monitor both the cluster health signal and also we also collect the constant signal to help us determine cluster healthy state. And more importantly, we build a proper service. As seen in this diagram, right? We call it service pinless. Basically, it runs at every AZ and send a continuous ping to every single Redis backend node to provide us an independent signal of the node healthiness, and also for example, sometimes we could have cross AZ network issue, right? This can help us to diagnose it very fast. Okay, I'm going to also talk quickly through our cost region cache service. This is actually a very interesting service. I hope in the future we can do a deep dive. So Uber runs with a multi-region architecture, and also cache is really important, right? It basically helps to share a lot of load. So in the catastrophic scenarios, we are going to do regional failover. We don't want to hit the code cache problem. That's why we're building this cost region cache service. So from a very high level, it has two components. The tailor components, which actually runs in the same host with the Redis node. And it basically hook up to the Redis process as a replica to get all the write commands. And then it's sent to a shared Redis cluster. We call it a string cluster because we send it to a Redis string. And then we have another service called string consumer. It's basically a microservice that pulls the data from the string cluster and then send to a destination cluster. So this works very well right now, but of course we have some thoughts. Can we make this as a native offering from the whole Redis Valkey architecture? Then it will help us to remove this particular string cluster and also simplify the architecture. Okay, the last part is the client. So Uber is basically has an architecture with many microservices, hundreds and thousands, and they all need to use cache. So there are many open source libraries available in the market. We have to we cannot build expertise on every single of them, right? So we have to choose a blessed library, and we decide to go with the Go Redis for Go and the Lex for Java. And then it's like we also need to think about how to simplify the experience for our product teams. Therefore, we build a wrapper on top of those open source libraries. So the library can help us to simplify the integration. For example, it can abstract the specific Uber internal cluster discovery protocol. And also it helps us to build out-of-box metrics for every single use cases. And it allows us to do better monitoring and alerting. And more importantly, it helps us to provide more advanced feature, such as circuit breaker, which is really, really important to prevent the cascading failure. And also we added context propagation and sharding features. So cache infrastructure at Uber is really important. And even though it's a cache that has fallback in most cases, but the fact is, if we have a huge, let's say, degradation on the cache, but in most of times the downstream cannot handle the load. Therefore, we have to make it reliable. And also, we do serve a really large scale, right? So we're a global company. So we also need to solve a lot of scalability problems. And those problems are not really easy to solve. And sometimes we do hit a hiccup in production. There are quite a few learning. And later, here, my colleague Shawn will going to talk about those learnings.
Okay, so next I will show some the lessons we have learned from our migration last year. All those problems happened based on our large scale services. We have so many issues have mitigated, and those are selected for something really interesting to be shared. And the first problem is so-called connection storm issue. This is something usually start from something small. At Uber, we have many microservices. Each service has lot of instance. Each instance running the Go Redis client. And the Go client connect to the Redis server node. And sometimes if the Redis server slows down or brain free becomes unavailable, then at that point, the Go client will begin seeing I/O errors. And in the Go client, those errors are fatal to the connection. So the client will immediately close the connection and assume this connection is no longer usable. And to proceed, the client will create a brand new connection and then retry those requests. And this actually creating a new connection to the Redis server, increase the pressure to the server. And now let's multiply this by hundreds or thousands or even 10,000s of instances, each of them failing roughly at the same time. So all those retries, they won't relieve the pressure to the Redis server. They actually amplify the pressure. So the Redis server, in this case, could hit 100% CPU utilization, stop responding to those clients. And even worse is there will be a feedback loop here. So all those new failures will result into even more new connection attempts. So this is a feedback loop driving the whole system into an outage. And in terms of how to mitigate this issue, we have basically doing three things. So number one, we want to mitigate this issue immediately. And how to do that? We have multiple approaches. We found the IP table rule is the most effective way. So we have an IP table rule applied to the impacted node. That rule will immediately stop cut all the traffic to that Redis node. and then it gives some room for the Redis server to recover. And it also stops the retry amplification. So this is a way we mitigate this issue. And secondly, for correctness, we upgraded the Go client from V8 to V9. So V9 provides some lot of improvements in terms of the connection. For example, the V9 removed the aggressive connection reaper, which like we found it causing the connection storm behavior. And also the V9 introduced fair queuing for the new Redis requests. It also introduced an explicit IO timeout, like independent of what the application gave. So by doing those together, we actually significantly reduced the connection time, improve this problem. And third part, we applied the circuit breaker and also a per node rate limiter to the clients. So this will effectively limit the retries new connection. And in addition, we worked with a customer to stop the aggressive retry and timeout configurations. So altogether, we turned this full blast outage problem into a recoverable event. Okay, and this is one form of connection storm. Actually, there is another form of connection issue we discovered in a proxy-based setup. So at Uber, we have L4 proxy in between the application and also the Redis server. So L4 proxy basically doing encryption and decryption. And what we found the issue is when, like normally this setup works fine, but whenever there is a burst of connections from one application, and then because the cost of new connection, like we need some CPU, we need memory, we need file descriptor setup for the new TLS connections, and then this will actually overload the proxy. And in some cases, we found the burst of new connections actually slows down the existing connections because the proxy like resource is exhausted on managing the new connections. And that point, the client will see the existing connections become slows down, and in the worst case, like timeout, and which again will trigger a lot of new connection attempts. So this is also another form of the feedback loop driving to an outage. So for mitigation, we made some improvements in the proxy. For example, we have some fairness algorithm inside the proxy to give the new connection and existing connection different priority. And we also made some huge improvement in terms of memory allocation, because sometimes the proxy spend a lot of time in memory allocation. And like we based on these two different kind of connection storm issues, that we might have a deeper question, like why we are having so much connections. This diagram actually demonstrates the relationship between the service and number of connections to the Redis server. So assume we have a stateless service. Each of it has many instances. Each of them running a Go client, and the Go client actually maintains a connection pool to the Redis cluster. And more importantly, this connection pool is per node, which means each Redis node will see traffic and connections from all the stateless service instances. Assume we have n service instance and maintain the pool size of P, then each Redis node will see n times P numbers of connections. With super large scale services, they might have like thousands of instances or maybe 10,000s of instances. So that will drive the per Redis node connection number super high. Like we have seen around 100K connections during the peak. And this is actually much more than the cloud vendor usually supporting. Like we typically around like 65K. So the high volume of connections actually driving the limit of the Redis server itself. Like we can see like 5% CPU increase just for the overhead of handling those connections, regardless of the regular traffic handling. And we also see like the client memory usage increase a lot under 100K connection. And also the Redis, the cron job spend more time like processing all the client's status, emits metrics, all those things. So this actually pushes the Redis usage into the limit. We have some way to mitigate this issue. Like sometimes we can do sharding. We separate different use cases into different Redis cluster. But I guess the fundamental problem is what's the relationship between the pool size and the Redis node. So if we increase the pool size, that means we will increase the pressure to the Redis node. If we reduce the pool size, Redis server will be happy. But what about the client side? So next slide, I will show another issue we found on the client side. So it's not, sometimes the problem is not happening on the Redis server side. Client side can have its own contention too. For example, like each Go client maintains a fixed number of connection pool. For example, 3 connection per Redis node here. And the problem happens when the application actually send a burst of commands. All those commands like targeting to the same Redis nodes. It could run a same key or could run different keys that hash into the same Redis node. And at this point, all those commands, the burst commands, they are queued up inside the client, waiting for the available connection to the Redis node. And so in this case, the Redis server may be still under light load, but from the application side, the user-facing side, we are start seeing timeout and performance degradation. So the connection pool can be too low, and it also can be too high. It's a trade-off between those. And for mitigation, we also have some way to optimize this situation. For example, we do some caching on the client side. So for some hotkeys, we cache the value. So for the jobs, they can reuse the local cache data instead of like sending a burst of commands to Redis. And we also do some deduplication inside the application, try to reduce the similar jobs, for example, cleaning up or whatever. So we dedupe all the in-flight jobs into one, so that reduce the burst of commands. And third, we found in some application use case, they send a lot of deletion for the same hash map. They may delete thousands of fields at one time. This usually happens like location-related stuff, like updating the driver information for certain location or something like that. So in that case, we actually do some optimization to batch all those deletion into a multi-key command, so that reduce number of commands from the application. So this is something we're dealing with to handle the client connection issue in the Go client. And alternatively, we also have some Java service. They use Lectus client. And that client has a I/O multiplexing. So it doesn't have this connection contention issue. So sometimes we also ask our application team to offload their burst traffic to Java services. And also this also lead us to see, explore the new Go clients, like how we would expect the new Go client can do the I/O multiplexing or either automatically pipelining, something like that. And in terms of our Java service, we also seeing some issues from the Java client. And for example, this is a very critical issue we have seen in the production. So sometimes the customer, they may have their own encoder. And then their own encoder function maybe throw exception in the middle. And as this diagram illustrates, initially the client, the application may send 3 commands, like to set and followed by a get. And the second set maybe have some issue, and then they throw a encoder exception. In that case, this set won't be sent to the Redis server. So in Redis, so actually the Redis server only receive 2 commands, and also it responds with for these 2 commands. But the problem is the client is actually expecting 3 commands. So that causes misalignment of the response and cause some data corruption to the application side. And sometimes we also see like off-memory can also cause the same exception and leading to the same problem. So for the mitigation, we first set up an alert to catch this kind of scenario. And then secondly, we work with our application team, share the best practice on how to set up their own encoder. And mainly we don't want them to throw an exception to break this queue. Okay, so with all those lessons learned in mind, and next I will show like our next steps. Okay, so what we learned from those issues is the cache platform is not only depends on the backend, it's actually a backend library and ecosystem work together to provide the reliability and scalability. And so for the backend side, for our cache platform 2.0 plan, we are still evaluating the Redis foundation, but we are moving forward to Valkey. And for libraries, as we mentioned, we are exploring the new clients which support multiplexing, have a better retry behavior and low latency. Also, for that, we want to build our ecosystem like with better guardrail and also provide best practice to our application teams. And while we're doing this, we always keep the scalability and reliability and performance in mind, try to optimize them as a whole. And for the next generation cache backend, we have 2 choices. One is Redis, like we are currently at Redis 6. So we can do Redis 7 plus, or we can also do Valkey plus. And here is something we really care about. One is the performance, second one is the client capability, and the third one is upgrade complexity, like how to upgrade from Redis 6 to the new version. And also the backend should be compatible with our control plane. Otherwise, we'll spend a lot of time on updating our control plane. The most important thing is the future sustainability. So we evaluate Valkey, and on the right side is what Valkey compare with those requirements. And we saw like Valkey can provide a very stable latency under stress, and it's compatible with Uber's standard client. And in terms of the upgrade complexity, it's actually similar by comparing Valkey and Redis. And for the control plane, we also found mostly Valkey is compatible with whatever we have right now. And the most exciting thing is like Valkey provide a good community support. So the whole community is growing, and we believe we can get a lot of benefit, and we can also contribute to the community. Like to finalize the talk, I will show our roadmap. Like see in 2026 this year, we are working hard on adopting Valkey, and we are also exploring the new client library support. And we're also considering developing a native cross-region cache service to reduce the blast radius of the regional failure. And by doing this, we believe we will have a cache platform to support our scale and also keep reliability and performance in mind. Thank you.